So now we come to the more important aspect of deep learning. More important or very important, whatever. We have defined this architecture, we have defined the full forward propagation, which basically means give me an image, I'll convert it into a bit vector, I'll send it to my many layers, I will apply a softmax, I will get a probability distribution, I will pick the maximum one and output that as my answer. This is what is my architecture for this particular problem. This is called an architecture because I have a certain set of layers, I have a certain functions in there, certain activations, all of that is part of my architecture. But what is not known in this architecture? The weights are not known. What are the weights? We have defined a symbol for the weights. What are the weights? Wi's and Bi's, right? Because at every step I am doing Wx plus B or W output of the previous layer plus B, nonlinearity. Now, how do I want to set these parameters? Let me use the term theta for all the parameters cumulatively. Theta is the superset of or the set of all parameters. How do I want to set this parameter theta? I want to set it such that it makes correct predictions, as simple as that. And what is this notion of correct predictions? Well, I am given some training data. So I am given that in my training data that I have this image, and for this image the output should be 1. I am given this image, and for this image the output should be 2. This is given to me. My goal is to find the parameters theta that allow me to achieve this. Okay? Question? Okay. Question. Parth asked, given this input, should y1 be maximum or should it be 1? If we are okay with maximum. Why are we okay with maximum? Because the way we are going to do the final prediction is that whatever has the maximum yi, we will just output that I as the answer. So even if it is not 1, it's close to 1, or it's just maximum, even if it's 0.6, as long as everything else is less, we will still make the right prediction. So we'll be happy. And that might still be okay, because it is possible that I have a certain symbol which is difficult even for people. How many times like somebody wrote 1 like this and it looks like 7? These things have happened. So sometimes people may be confused. The training data may be ambiguous. The training data may be incorrect. There may be noise of various kinds in various parts of the process. So we don't want to push it to 1 and force the networks to learn more than what we need. Because by forcing it, we might end up making the network less generalizable. Right? So we are satisfied as long as yi is maximum. Right. So what's your name? Chanakya says, what happens when yi is less than 0.5? Even if it's maximum, let's say, because it's a 10-way classification problem, let's say everything is 0.05 except, or let's say everything is 0.08 except 1 is 0.28. What would we output? 0.28, the one which has 0.28, that is what we are going to output. Are we happy with it? Probably not, right? We may not be happy with it. And when might these situations occur? When I don't even give a digit as input. I draw a random character and give it as input just to test the system. Okay, which digit will you recommend now? I am giving you the symbol X. Right. So if you start playing with neural network like that, obviously the neural network will say, look, I only know, my world is about digits. I only know that much. So I will output a probability distribution. It is possible that all zi's are low. But then when we do softmax, they become relatively uniform. In which case, what will my system output? Is still output the number which has the digit which has the highest probability. If we want to allow for such a possibility, we would allow for a no output as one of the outputs, none of the 10. And then we will have to train it for it. So we will give it random images and we will say, look, this is not anything from 0 to 9, this is not anything from 0 to 9, it's none of the digits. And then we will hope that one of the answers would be higher probability. But for now, we are just going to enforce that the maximum should be what we are looking for, okay, even if it is less than 0.5. What if 2 yi's have maximum value, right? That's another question. What happens? Okay. First of all, can it happen? Well, it can happen with an extremely low probability because these are weights which are completely trained by the system. So the weights may not be exactly the same, and because of which there may be small variations in 4th digit, 5th digit somewhere, and so you will output that. But more importantly, suppose 2 of the digits are 0.45 or 0.44 or whatever it is. What does that tell you? That tells you that the model is confused. That tells you that, look, the model is really confused whether this is this digit or that digit, and then use that information downstream. You can ignore that particular digit, you can ask humans for that particular digit, right? You can do whatever you want to do with it, right? So, but for now, again, this is deep learning 101, right? So all your questions are sort of valid, but in practice we are just comfortable saying, I want the max to be the correct answer, and I want to find those parameters theta which let me achieve this. Now, I am given some training data. So I am given this kind of training data. We will call this XY pairs. So this is my X1, Y1. This input should lead to 5. This input should lead to 0. This input should lead to 4, and so on and so forth. And now I need to somehow use this training data to find the best network parameters. And the fundamental concept that we are missing is what is called the loss function. So what actually happens is that you have some parameters, current parameters. You take a particular training example as input, give it to this neural network, and have the neural network produce a probability distribution. So it produces a probability distribution. Now I will say that given a set of network parameters, the probability distribution that I output, I can compare with the true label. The true label would be the y1 for the example at hand, like for this it will be 1. And then I would say, how costly is this prediction? How bad is this prediction? Am I satisfied or am I not satisfied? For example, this is my target probability distribution. And this is the computed probability distribution. Now, are you satisfied? No, you are not satisfied. So what do you want to say? You want to say, look, I am not satisfied, you should be given high penalty for such parameters. And now you have to define such a function which can give high penalty for such parameters. So one such function would be simply squared loss. That I do 1 minus 0.2 whole square plus 0.3 minus 0 whole square plus 0.5 minus 0 whole square, and sum that, right? But sometimes it can be more interesting. Squared loss does not work for probability distributions as well. We have something called the cross entropy function. For people who are interested, they can go and read it out. It's the way to compare two probability distributions. So, nevertheless, the point is that this computes a loss function we will call L, a cost function we will call L. And this L is a function of theta, because I use these thetas to compute this prediction, which I compared with the true to get the final loss. If I had a different theta, I will have a different loss. So finally, what do I want? I want those parameters theta that minimize the loss. So therefore, what have we done? We have taken our neural network and we have converted the training problem, finding the parameter problem, into an objective function that we can minimize. Now that shouldn't surprise you, because even in base nets, that's sort of what we do. Even in RL, when we did sum of basis functions, that's sort of what we did. We defined the squared loss and said, let's take the derivative. That's exactly what is going to happen. And again, it should not surprise you also, because I told you, alt learning is nothing but some form of optimization. And it will have a form like Wi is equal to Wi plus something. It is always going to have that form. Wi is equal to Wi plus learning rate times something. Right. Okay. Now I am given many training data points, and for these many training data points I can compute many loss functions. So we use the term y1 is the true label and y hat 1 is the predicted label or predicted probability distribution. So for example, in this case, if the input is 4, that is x3, if the output, whatever is the probability distribution, that is the output, that is y hat 3, and then the final target is y3, and then there will be some loss between the two. And so I add over all the data points. This is typically done. We take each input as independent, and their contribution to the loss function is independent. Okay. So find the network parameters theta or theta star that minimize this particular loss function. That is sort of our goal, and we can do this by gradient descent. Right. So how do we do this by gradient descent? We have some loss function, we have some parameters theta, we can compute the derivative, we start from any random theta, and then we try to move in the direction of the gradient or opposite the direction of the gradient, because we are minimizing, and we keep doing this, keep doing this, keep doing this, and eventually we will get to get somewhere close to the minima. So all of learning, modern learning, continuous variable learning is nothing but some form of gradient descent. But of course, would it lead to global optima? In general, no, and in fact for neural networks almost never. And the reason is that because I have layers of these neurons, and each layer has an activation which is not necessarily convex, but even if it is, the combination of these convex, because the output goes into the next and so on and so forth, makes a highly nonlinear function. And in fact, this is the typical nature of the nonlinear function, and so the final theta that you get is some local optima. Okay? Depending upon where you start, you reach some local optimum and you get different results. Okay? But we are not afraid of non-convex loss functions, and this is just the beauty of AI. The theoretician says you cannot reach global maximum. We say fine, we'll just do whatever we can with local maximum. This has been there even in local search, when we did local search in the AI class, and this is also true in the context of neural networks. So we come up with strategies where we can find better optimum or better optima, but we don't care if we don't. We just keep trying to improve it. We train it many times from different starting points. We do whatever we can, and finally we get a theta star, which is the best so far. We just tell the applications people, look, we have trained a great neural network. Now you go and classify your images with it or whatever. Okay? And it is not just local maximum or local minimum, pretty much not different from what we studied in the local search class. Yes, we could be stuck at local minimum, but we can also be stuck at saddle points where we can make a move, but the derivatives will be 0. We may be stuck at we may be very slow on plateaus, and so on and so forth. And there are lots of even theoretical investigations that are going on how not to how this may not happen and what to do. But we are not going to talk about this. You should, at some point, I encourage you to take a deep learning course where all these things which I am describing in 2 to 3 minutes will be described in 1 to 2 lectures. Okay. Then the next very important phenomenon is the phenomenon of mini batch. Because we will typically have many parameters, we will have large training data points. If we have too many training data points, then going over all the training data and computing one loss function by doing summation over R, LR, and then taking one gradient step might be very slow. So what we do, we typically say, okay, which GPU do I have? I have a 32 GB GPU or a 16 GB GPU or an 8 GB GPU. Okay, fine. How many training data points can I fit in my GPU so that each matrix computation gets done in like unit time? Okay. So, the system says maybe 128. So, we say fine, we will just divide the full data into pieces of 128 data points each, and we will call each of that group as a mini batch. And then we will give this mini batch to my GPU, it will compute all the parameters, it will take a gradient step only on those 128 data points. So, now I have changed my theta. Then I take the next 128, give it to the GPU, then I get the next theta from theta 1 to theta 2, then I give it the next, then I go from theta 2 to theta 3, and I keep doing this. At some point I am done with my training data. What do? Start again. Maybe if I am smart, I will redivide them into a different mini batch combination, or I will just say forget it, I will just give the one mini batch again, then the second, so the same first mini batch, the same second mini batch. Going over training data once is called one epoch. One epoch goes over many mini batches and does many gradient steps. Okay. So, again just to go over the slides, randomly initialize theta 0, pick the first batch, compute the loss only on the data points that are in the first batch, do a theta step, gradient step, then pick the second batch, do the next same thing, pick the next theta 2, and keep doing this. C is different each time when we update parameters, the data points on which we update is different. And the extreme case of mini batch is what is called the stochastic gradient descent, where in the extreme we only take one data point. But mini batch is only somewhere in the middle, right? So, if we really did gradient descent, what will happen is that our gradient would be better computed, obviously, because you would have gone over the full training data. On the other hand, if I am doing stochastically, if I am only doing it on a small training data, then I may be going everywhere, and I might sometimes be going in the wrong direction because it is not giving me the correct gradient. On the other hand, if you plot the time versus cost curve, then each gradient computation will be very slow, because you would have to go through the whole training data, and after that you will make one move. So, for a long time you will not do anything, then you will make a move where your cost will increase or reduce. Then for some time you will do gradient computation, and then your cost will reduce. So, this is the kind of curve you will get when we are doing gradient descent. On the other hand, if you are doing stochastic gradient descent, you will start one data point, quick compute gradient, move, another data point, compute gradient, move. You will be making very fast moves, but your cost will be decreasing slowly. So, which one is better? Well, in questions like this, typically the answer is, it depends. When you go to your interview next year, you have a job interview, and the person asks you an interesting question, is A better or B? You must say always, it depends, but you shouldn't stop there. Almost everything you will be able to find a reason to like. Same with people. They always have some good qualities. So, in the case of gradient descent versus stochastic gradient descent, it has been found that early on in the training, stochastic gradient descent is really, really better. But later down the line, gradient descent is better. But because we have large training data points, we are almost never in this region of the curve. So, we are almost always in this region of the curve. So, in practice, nobody uses full gradient descent. They all do a mini batch based on the GPU limitations, and they do stochastic on that mini batch. Okay? Or gradient descent in the batch, and then stochastic across batches, basically. Okay. And that is it. So, then I think, yes, so this is faster. Until all mini batches have been picked, you do this, and this is called one epoch, and then after this you repeat the above process, and you may shuffle your training data. Yes, question?
So if you have a lot of GPUs, then...
Yes, so the question then above asks is, if I give you lots of GPUs, can you parallelize this computation? And the answer is yes, you can. I would also say that that programming becomes much harder for novices like you, but also people have found that in some cases it really helps. In some cases it is not clear how you deal with the different GPUs, because what is actually happening is that now what you are saying is that theta 1 goes to theta 0 minus this is parallelized. So that means that your first processor sent you some theta 1 which it thinks should be the next theta 1. Your second processor sent you another theta 1 which it thinks should be the right theta 1, and all your processors have sent you many theta 1s. Now you need to figure out how to combine them. Moreover, they may not do it synchronously because one processor was faster for whatever reason, one was slower, whatever, right? They may send you these theta i's asynchronously. How do you deal with this becomes a challenge. However, all of this said, the most famous, not necessarily now the state of the art, but one of the most famous good deep learning algorithms for reinforcement learning is what is called A3C, and the first A stands for asynchronous. So essentially what you do is that different GPUs are doing their computations and they are sending the next version of their weights, and you are asynchronously computing them and updating your weight vectors and hoping that everything converges. It's a complicated mess, but there is a lot of research that goes on into this area, and this area is called distributed machine learning. Very important area, right? So extremely important in today's world. Okay.